resist, photoresist. All right. Right, can you see my screen with the slides? Right, cool. So let's move on with lithography part 2. So today we're going to talk about resist performance factors, okay, and a few other stuff following this. So there are a few there are a few factors of the resist that can affect performance, okay. So for example, resolution, we've discussed a little bit about resolution in the last class. We've also discussed about DOF, right, depth of focus. We have also discussed about factors that could contribute to resolution and DOF, and how do we um, improve the resolution and improve the DOF as well, right? So resolution is the first one. Addition of the resist is another important factor. So you want the resist to adhere well to the surface. So that's why we apply HMDS, hexamethyl desilazine, during the priming process, during priming steps, before we spin coat the resist on the ADH, right? So module ni kita panggil ADH, usually in the lithography process, and that is addition. And then the exposed rate, sensitivity, exposure source. We've discussed briefly about dosage. We've discussed about focus, right? And then we've discussed about the wavelength of illumination that we will use, whether it's DUV or I-line or ARF or KRF or down to EUV, for example. And then we've also discussed about process latitude, which is essentially process window, right? So now you already understood that you want to have a very wide process window or very wide process latitude, where you can have fluctuations of certain parameters without affecting the results so much or significantly. For example, we discussed about the CD, right, which stays stagnant quite in a wide range of process fluctuations. And in other case where you will have a steep change in CD, for example, if you are talking about CD, when you have varied focus or varied exposure dose. Okay, so essentially we want to have a very wide process latitude and process window. And if you have a very wide process latitude and window, you can say that your process is stable, okay, upon undesired changes in your process parameters. And then pinholes, when you spin coat your resist, you don't want to have pinholes. If, for example, pinholes, let me sketch here. So this is your wafer, silicon, for example, if you have a resist on, so when you sponge your resist on the silicon or on oxide, so assume oxide kat sini. So this is your PR photoresist. So dekat some area tu, you akan ada pinhole. This is unintended, right? You don't want to have this, right? Ada lubang, ada air column, right? Air column. So essentially air lah. Maksudnya dia tak cover the whole surface. Kalau you tengok wafer tu, wafer from the top, yang bawah ni from the side cross section, kalau atas from the top, then you will see the whole surface is covered by the resist, except maybe you can see one bubble. Okay, bubble tu is the pinhole. Maksudnya kalau you send this wafer under the microscope, then you'll see air bubble kosong that resist. Could be small or it can be hundreds or tens of microns, depending on the nature of the pinhole. You don't want this to happen, right? Particle contamination levels are also associated with the resist. You don't want the resist to have defects, okay? Essentially, you don't want any defects at all, but if there is defects in the resist, so you want defect level to be within control, okay? So this can be scanned. You can scan for defects. ada equipment yang you can scan the resist punya ni, you will see some dots or something. Then the system will help to categorize the defect or the particle by the size, by the areas, and so on and so forth. Step coverage. We'll talk about step coverage, especially if you are coating the resist on features, on features, okay, on features that are already existing, that already exist on the wafer. Contohnya you dah ada features in the previous layers, and then you want to spin coat your resist. Okay, somehow the morphology, the conformality of the resist will be affected by the underlying layers, right? Step coverage. So essentially, you want the step to be the coverage to be perfect, right? Then thermal flow of the resist, especially related to the maximum temperature the resist can stand, right? Because we have been talking about soft bake, hard bake, PEB, okay, in order to drive off the solvent, to make sure that your features are strong, addition is good, and you eventually end up with the intended features as printed. Okay, so it's related to the thermal flow. So resolution, the smallest opening or space that can produce in photoresist layer. So we talk in terms of equation, K lambda over NA. Okay. I want you to go into the go to the textbook and look at examples of calculation. Try to see how do you do the calculation on resolution and DOF, okay, with the given parameters. For example, K is given, illumination wavelength is given, and NA is given as well. So how do you then calculate the resolution? How do you then calculate DF? So what do they mean, okay, in terms of the process performance? So related to process, particular processes, including exposure source and developing solution, yes. Thinner layer has better resolution, okay. Thinner resist layer has better resolution. And normally, if you wanna print advanced technology nodes, so the nodes can be printed if you, well, they are usually associated with thinner photoresist. So kalau layer yang tak berapa kecil sangat, then you are using normally thicker photoresist. Okay, so I think I still remember last time when we run front end layers. I think the thickness is somewhere like 18,000 angstrom, 1,800 nanometer. Okay, 1,800 nanometer in this case of resist thickness is considered as relatively thick. If you want to talk about thin, then it's in the region of 500 nanometer or lower than that. Etch implantation barrier and pinhole free require thicker layer, so that's why you need to optimize the thickness according to what you want to get. Okay, positive resist has better resolution due to smaller size of polymer. Okay, so a bit of comparison between positive and negative resist in terms of polymer that's used, a photoreaction inside the resist. Okay, we've discussed quite a bit on polymerization and solubilization that makes the negative gets harder upon exposure and the positive gets soluble upon exposure. Then sensitizer being used inside the polymer, and then additive. So there are two parameters used to define properties of photoresist. The most critical one, contrast and critical modulation transfer function, CMTF. So what is contrast? Contrast is the ability of the photoresist to distinguish between various levels of light intensity. Okay, apa maksudnya? How do you relate this to, okay, how do you relate this to the exposure process? Okay, by sketch, this is what it means. You have silicon, and then you have your resist on, and then you have illumination wavelength coming through the reticle. Okay, reticle. And then the transparent area is the glass area, and this is opaque, typically chrome, usually chrome. We've discussed this while discussing reticle last time. So in this case, if you're using a positive resist, for example, then this central region will be soluble eventually, right? And the contrast in this case is the ability of the resist to distinguish between various levels of light intensities. So, kat mana you nak tengok kalau dalam sketch ni, where will you be interested to see the various level of light intensities in particular? If you look at the resist cross-section, kat mana yang paling penting? If you want to relate to this, distinguish various level of intensities. Kat mana? Anyone? Where is the important border that you want to see? Anyone?
Dekat tengah kau ada.
Dekat tengah, okay. Tengah dekat mana? Tengah. Dekat tengah, betul-betul tengah ke? Ke dekat tepi dia? Kat area sini ke? Any specific area? Kat mana kita nak tengok, kita nak relate various level of light intensities yang resist perlu differentiate.
In the border.
Dekat border, right? Kat border. Sebab apa kat border? Sebab apa Faris kat border? If you, kita zoom in kat sini, kita zoom in this layer je. Kenapa border, Faris? Okay. Ni yang expose. Right. Kenapa kat border? Kenapa kat border yang penting in this case? By border,
Sebab dia light sensitive polymer.
by border you mean this X, right? This negative X and X, right? It's just label je lah, nak lebih senang nampak. Is it?
Yes, Doctor.
Okay, right, correct. Dekat borders, the two borders are very, very important in this case for contrast because tengok balik light coming tu from the illumination. So, dekat sini, dekat tengah, resist are experiencing full illumination, right? So, full illumination kat sini. Tengah ni full illumination. Tiba-tiba dekat tepi dia yang chrome tu, tak, does it experience any illumination at all? Zero illumination kan? So the light intensity at the border suddenly change. Okay, from if you want to compare 1 to 0, okay, dekat tengah ada exposure because of the transparent area in the reticle, and then suddenly sebelah dia tak ada exposure at all because the chrome is up there and the light is being blocked by the chrome. So dekat sini, dekat tepi ni will be very, very crucial, the borders. The border of exposed and unexposed regions, okay? So we'll see later on, what does this mean? It is experimentally determined by exposing the resist to differing amount of light developed for a fixed time, measured thickness, blah, blah, blah. Expose lah, technically you're exposing the resist and you see what happens next in the features. All right, so let's relate this to the borders. Okay, patah balik kat border ni. So we've discussed before this that you want to print, ideally you want to print a square shape feature, right? But it's just not possible due to limitations of optics, photoresist and reaction and blah, blah, blah. So you're going to have some positive profile on the sides, okay? So let's go there and try to understand. All right, so if you look at the positive resist on the left, okay? Relate balik dengan mechanism, So this is to illustrate the concept of contrast in the resist, positive and negative. Okay, so let's look at the positive. This is on the y-axis is the fraction of resist remaining. Okay, fraction of resist remaining, and then on the x is the exposure dose. Okay, on the x is exposure dose. Right, QF in this case. QF ni is the minimum dose required in order to render the resist to be completely soluble. okay, in order to induce the resist to be completely soluble. Okay, remember last time I talked about you need to expose the resist for it to be soluble, but that's not specific enough. You have to expose the resist with an energy of more than or equal to the minimum exposure dose, right? Minimum exposure dose. So in this case, you can see minimum dose lah. Just put it minimum dose. So when you expose the photoresist with more than 100 millijoule per cm squared, more than 100 millijoule per cm squared, and then you develop the resist. So let's relate this back to CED process. Coat the resist, expose the resist with the right dosage at the right areas, and then develop the resist with TIMA. Okay, so that some areas will be soluble and some areas will not be soluble. So in this case, the areas that's supposed to be soluble are on the right hand side. Okay, maksudnya apa? Kita tengok kat sini, fraction of resist remaining. Maknanya kalau lepas CED tu resist dah tak ada kat situ. Dia dah soluble kan? Dah soluble and they are removed already. So resist remove. PR completely removed. So you tengok kat sini, the graph though, it shows 0, isn't it? Fraction of resist remaining is 0, so that means there's no resist left. Remove completely. When the Q, if you like, Q is more than QF or equal to QF, 100 millijoule per cm squared. So what happens when you have your energy lower than QF? Maybe energy lower than QF already. So say when your energy is between Q to Q naught, katalah 0 to Q naught, apa jadi? Kenapa kat situ dia punya fraction of resist remaining equals to 1? Any idea? Or indirectly that says that there's no resist remove at all.
No resist remove at all.
Kenapa? Kenapa tak ada resist remove lagi? Between
Sebab energy of exposure dose tu tak cukup untuk remove dia.
Yes, exactly. Good. So if you go back to the comparison, tadi kan, tengok photosolubilization kan, satu photosolubilization, satu polymerization. So now we're talking about positive resist. So photosolubilization, right? So in this case, when you're exposing your resist between 0 to Q naught, Q0, Q naught, so the energy is not enough to induce photosolubilization in the photoresist. So bila you buat CED, bila you develop the resist using TIMA, you will still see the resist remaining. Maksudnya bila you ambil resist kat portion ni, you don't buat cross section, you will see the whole resist still there. Okay, sebab energy is not enough, so technically nothing is happening inside the resist, even though you have exposed the resist. So this is what you should expect if the exposure dose fluctuates. Kalau tiba-tiba exposure dose rendah for some reason in the scanner, then you will see the resist will be left on the silicon. Okay, so energy is not enough. So that's what you will get. This one, okay, resist left fully. On the other hand, when the moment you hit Q naught, dia kata your energy sekarang Q naught, so how much is Q naught? Say, okay, log scale, say that's 5, maybe 5 millijoule per cm squared. So the moment you hit 5 and above, so if you do CED, what you'll see? You are now in this region between 5 to 100. Bila you buat CED after development, what do you see? Kalau kita discuss cross section ni, what will you see from the cross section of your resist? Anyone? Come on, go. What you'll see, go. Between Q naught to QF in terms of the cross section. Anything? Smaller. What do you mean smaller? The resist becomes smaller. Menipis, right? Smaller, smaller menipis, depending on your dimension that you're trying to explain. So you'll see some of the resist left and some of the resist that's supposed to be removed are still not removed. Maksudnya mungkin you punya, katalah you supposed to remove so silicon, say supposed to remove okay lah, you might want to remove like that eventually. Tapi you still have this left. You want to have something like that eventually. Okay. So the other tapi tak fully remove because the energy is again not enough, not exceeding, not up to the minimum energy required in order to induce photosolubilization, right? Quite muffled. Right, so the moment you hit 100 millijoule per cm squared, then only you get your resist removed. So kalau remove je lah in this case. So kalau you nak dapat feature ni, then you're gonna get that feature eventually, right? So that's what happens when you talk about positive resist. On the other hand, let's look at the negative resist. The very same situation is just that they are opposite, okay? So negative resist, on the other hand, remember the mechanism is polymerization, cross polymerization, when the energy that is used for exposure is equal to more than to be able to induce polymerization. So in this case, let's have a look at right, fraction of resist remaining. Okay, can they are 0 to Q naught? What happens if you exposed your features, your resist below Q naught? What's gonna happen? Fraction of resist remaining is 0. Apa jadi? Come on, anyone? At this point, within this range, what happens? Will you clear ni? You'll be clear of the whole mechanism. Okay. 0 to Q naught. What happens? Fraction of resist remaining is 0. That means after your CED, what happens? What do you expect to get on the silicon? Anyone? You dah code, you dah expose, you dah develop, then what do you get? This soalan applies here based on mechanism that you have understood. Izati. What do you expect to get, Izati? Between 0 and Q naught. Izati? Kali? Anything? What do we get? Tengok why is this? Oh? It's very straightforward, right? The description. Fraction of resist remaining equals to 0. Meaning nothing. Okay, nothing means what? Nothing about? Nothing is left. No resist left, right? Fraction of resist remaining kosong. Maknanya apa yang you code, you expose, you develop, you wash everything away. Ada resist yang tinggal pun. Right? Remember, negative photoresist, you want the features to be maintained, right? To remain on the on the silicon because you have hardened the resist which define the features. But in this case, nothing left. It's about energy tak cukup. Okay. Kalau tadi positive resist semua ada lagi. Tak ada apa pun remove sebab tak ada solubilization at all. In this case, there's no hardening at all. Semua jadi lembik lah. You basuh, you wash, you develop, semua keluar. Right? So that's what essentially happens. The moment you hit Q naught to QF, apa jadi? So you will start seeing some resist macam tadi juga, macam tadi. Tapi the reverse lah. So you want to see, say, perhaps CD of 100 nanometer, but you'll be getting 70 nanometer or 40 nanometer or 30 nanometer while you're expecting 100 nanometer. So you're expecting more, but you get less because not enough resist hardened. Okay, so that's what you get. So you're going to get some fraction of the resist left on the silicon. So the moment you hit, say, close to 100 or about 100, let's just assume it's 100, easier. 100 millijoule per cm squared for full polymerization for it to fully harden. Then only at that point you'll get the whole structures to be well defined. Okay. Maknanya waktu tu baru penuh, waktu 100 millijoule, then you'll get your whole features to be ready. Okay. Done. Okay, is it clear on this graph? Is it clear? So camera 3, video 3. Is it clear? Okay, paham? Right, good. All right, normalized resist thickness, ini sama yang macam tadi ya. Normalized resist thickness up to 1 on the y-axis, and then the dose that you need to use in order to clear the resist, for example. Okay, so in this case, if you're talking about positive resist, ini positive resist, right? Remember the curve, positive resist in the curve. This minimum resist that we label as QF is called dose to clear. Okay, dose to clear. Minimum energy dose or minimum dosage required during the illumination in order to completely induce photo solubilization in positive resist. So that area yang tak ada resist memang kena tak ada resist. Okay, maknanya kita clear lah, dose to clear. Nak clear area yang tak perlu ada resist, nak clear. That's what it means, right? Kalau area yang ada resist, for example, your contrast curve, this is called contrast curve, right? Your curve says like that, for example. Ada value lagi kat sini, for example, contoh. So that means this resist will not be cleared yet. So that's not dose to clear, right? So kalau you ataupun you ada this curve and then you adjust your dose to be here, then you should expect that some portion of the resist will be left because of incomplete photo solubilization in the resist, right? So that's what it means. So the slope determines the contrast and the dose sensitivity. Okay, the slope. So it determines the contrast. So this is the contrast curve. Okay, kalau negative resist, then it's going to be something like that. Okay, reverse here. Contrast curve, dose to clear. For positive resist, material exposed to low light will not be attacked by the developer. Material exposed to large doses will be completely removed. So just what that means is this curve. Okay, so kalau you operate kat sini and you operate kat sini, two different points. So small one and more than enough, right? Intermediate doses will like partial removal. Okay, if you're operating here, say it's not up to the level of dose to clear yet, it's not up to QF. So some of the resist will be left, some of the resist will be removed, depending on how far are you from the QF. The contrast is the slope of this curve, and that's given by slope equals to 1 over log QF over Q naught. Okay, so go back to the curve, mana QM, mana Q naught. Okay, that's the one. So QF over Q naught. So that QF, Q naught. Oh, Q naught, sorry, bukan F. QF over Q naught. Q naught is the initial, QF is final. Itu. The typical G line and I line will achieve a contrast of 2 to 3 and QF values of 100 millijoule per centimeter squared. So I remember last time when operating DUV, I think the dose is somewhere around 30 plus, if I'm not mistaken, 20 to 30 plus for DUV. I don't remember exactly, but I think it's somewhere in this region, right? For it to completely clear the resist, okay, or those clear minimum. The contrast is not constant, but depends on process variables such as development chemistry, bake time, blah, some of the factors throughout the 8 steps, right? It's desirable to have a high contrast as possible in order to produce the sharpest edges in the developed pattern. So remember, the slope is the contrast, okay? Slope is the contrast, so that means you will actually define your punya patterns will be following the contrast curve, more or less, okay? So you want to have high contrast, so that means you want to have a very high slope as possible in order to produce the sharpest edges in the developed pattern. So case 1, case 2, case 1 like that. Case 2 like that. Okay. Yang mana better contrast? Case 1 or case 2? Which one has higher contrast? 1 or 2? That you want to have in your features. Which one has higher contrast? Anyone? Write down in the chat box. One or two, higher contrast. Mana higher contrast? Ada jawapan apa ni? Satu kah? The slope determine the contrast. Which one has better contrast? Higher contrast? 1 or 2? So dua orang jawab 1. Sorry, 1, 1, 2. 1, 1, 2. Ada lagi yang lain? Two. So if this is your features that you want to develop in the resist, which one would you like to have? Would you like to have resist profile like number 1 or like number 2? Number 2 juara. Ada lagi after juara? Anyone else? Let's have another 2 guesses. Slope is contrast. And you want to have high contrast. So you want to have high slope. So which one has high slope? Satu ke dua? Dua kan? Okay. So just imagine this contrast curve as your features, as your resist that you will eventually develop after CED. Okay, kalau you ada macam profile that is too positive, kembang kan? So you won't be able to measure your CD correctly because tu ada algorithm lah. Dia ada algorithm measure kat atas, ada algorithm measure kat tengah, ada algorithm measure kat bawah while measuring the ICD cross section. So you will get 3 different DICD kalau dia besar macam tu. Dan kalau you measure CD nanti guna SEM, kat atas dia measure this much A, and then you measure tengah B much bigger than A, C kat bawah sekali much bigger than B and A. And then pening dia nak average lah. You measure something that is close to square, slightly positive, then it's going to be more straightforward for the ICD. Right. Next, contrast. Yeah, aerial image pretty much. Example of how the quality of the aerial image and resist contrast combine to produce resist H profile. Okay. The left side shows a sharp aerial image. Tengok yang kiri, sharp aerial image. Tengok ni ya. Oh, sorry. Sharp aerial image and steep resist edges. Okay. Tengok dia punya gradient is very high. And the area that it expands, yang jadi positif tu, is very, very little. Maknanya, dia tak kembang sangat lah. That's what it means. The example on the right shows a poorer, okay, poorer aerial image and resulting gradual edges on the resist profile. So this is called sharp on the left, poor. Okay, kita nak yang macam kiri ya, sharp. 145. Let's go for 5 minutes. So those are the QF and Q0 and right. Okay, compare. MTF defined in 2 points in the photographic system. MTF is modulation transfer function, measure of how the dark versus the light intensities in the aerial image produced by the projection system. On the other hand, CMTF is measure of the exposed versus unexposed region in high contrast image focus. Ini kita buat calculation dan menempah. And that's defined by QF over Q0. Okay, QF minus Q0 over QF plus Q0. So as long as you know the dosage, the minimum dose to clear and then your initial dosage Q0, you can then calculate the CMTF. Is a minimum point of optical transfer function necessary to resolve a pattern in the resist. So resolve a pattern here means, maksudnya kalau you punya pattern is too close. So kalau tengok dari atas, this is your wafer, tengok dari atas, then you zoom into the patterns. You remember we can print lines or holes, right? So kalau you print lines, contoh macam ni this one line, and this is another line on the side. So dua line, dua line macam tu. So it's rather easy for you to resolve the lines if the lines are big and widely spaced. And jauh lah dia antara line ni dengan line ni, the distance we call that as pitch. Okay, pitch. If you are in litho, then you learn all this pitch stuff from dia punya profile. Kalau tengok daripada cross section lah, pitch from the first point to first point. Baru dah naik tu raise punya apa ni, increasing punya slope tu. So that to the next one is called pitch. Okay, if the pitch is very small, so that means the lines will be very closely spaced. But it's hard to resolve the patterns if the patterns are not sharp enough. Maksudnya kalau you punya pattern tu kembang, kalau line rapat, then kalau you tengok di tepi, you're going to get like that, right? Kembang, and then dekat sebelah tu dah ada kembang. Ada another line yang sama juga. So maksudnya it's like trapezium there, turun, naik, balik, tiba-tiba dah naik dah trapezium tu. Right? It's not well resolved. Okay. This is the problem when we talk about advanced technology node. Sebab dia punya pitch is very small. Dia dekat dekat dan packed. On the other hand, kalau you cakap tentang teknologi yang dah lama dan they are widely spaced and they are big, then it's not so big a deal. Okay, in terms of contrast. Kalau you cakap tentang high technology, the contrast will be very, very crucial because they have to be, we need to resolve the two lines clearly. Right? So that's what it means by resolve a pattern. Tak boleh beza lah kalau dia we cannot resolve the pattern, that means line tu terlalu dekat, you cannot differentiate, and when you want to do the measurement system cannot tell where's the line, where's the space, where's the pitch, cannot. Okay, that's why you need to have a very good contrast, a very clear cut, square shape. So that's what it means. Effect of resist thickness. Resist usually do not have uniform thickness on the wafer. Right. I talked about it just now, where if you want to spin coat your resist on existing features, okay, your wafer dah ada this kind of trench, for example macam longkang, tapi dalam dia longkang, tapi but then in the wafer fab process we call this as trench. Right, there's one process step in the front end of wafer fab that's called STI, shallow trench isolation. Tapi longkang ni kita panggil trench. So if you want to do lithography on the existing trench, it's going to be super challenging because you have to spin coat the resist uniformly across, including in the trenches. You'll probably have hundreds of thousands or millions of trenches across the wafer. And it's very, very difficult to cover the resist uniformly because naturally that's what happens. So it will just flow into and cover sikit-sikit. So this is what normally happens, right? So you have to ensure that the resist is well covered. So yeah, this is step coverage issue. Step coverage. Mana bila ada step, ada lubang, dia tak akan cover well. Unless you have to make sure that your recipe, your coating recipe, need to do this well. Okay, mana bila you develop the recipe, sebelum you release for mass production, you have to do the cross section on the planar areas and also on the trenches and see how good is the coverage of the resist based on the recipe created. Okay, so kalau tak okay, kalau you nampak step coverage ada problem, then you have to tune the recipe so that your step coverage improves, okay, to a tolerable level. And then one more thing, we have edge bead. Bila you spin resist, this is a problem in the quarter cup. So let's finish in like 2 minutes. Yeah, 2 minutes. Let me finish this page. This is your wafer, for example, on the top. Jadi di atas wafer macam ni. So bila you spin, you dispense kat tengah kan, your photoresist, then you spin. Then the resist will be distributed according to the force. Okay, they can send outwards, right? The force, so they can distribute. Bila dia distribute, kita tengok wafer ni dari tepi. You take that wafer and say, this is the wafer, for example. say this is the center of the wafer. Now illustrate the edge bit problem, and this is the edge of the wafer. Bila you spin at high speed, what happens to the resist on the edge? Dia akan jadi thickness dia akan maintain, tapi bila hujung dia akan jadi kembung, dia akan jadi bit. Right, so say this is your wafer from the side cross section. So ni center, kat tengah C center, EH, EH, EH. So what will happen is your resist will be coated across the wafer merah ni. But towards the end, due to the distribution of the resist, you're gonna have bit. Dia akan terlebih hujung ni sebab dia spin kat hujung kan. Dia semua stand to the edge. So dia akan jadi bit. Jadi kembung sampai ke bawah. Dia ada surface tension. This is dangerous. Sorry. This is dangerous for robot arm. Bila you ada robot arm nak ambil pinset tu nak ambil wafer. So we had these issues a couple of times last time. Before the robot arm picking the wafer from the coating module, this bit needs to be removed. Dia kena potong, kita akan ada chemical untuk remove. We call that as EBR, edge bit removal. So dia akan ni wafer, dia akan dispense chemical on the side, and then dia akan spin. So dia akan cuci keliling, cuci. So this bit will then be removed. Ni wafer, then coating you kat tengah je. Bukanlah kat tengah, sampai dia tak cover sampai hujung lah. So that there's some space here. Because the moment robot arms comes in to pick the wafer, they kena pick the exact size of the wafer, which is the wafer size, original wafer size. Kalau ada bit kat tepi, then the wafer size increases by some magnitude. Dia ada tambah size. Bila tambah size, then wafer placement will not be good, and maybe pernah jadi last time, ada edge bit removal not working fine, and then bit terkumpul kat hujung, then pinset ambil wafer drop. But it doesn't sit properly because of the bit. And then some cases, bila bit tu is made of polymer, right? Polymer tu is a bit sticky, and then dia akan melekat dekat robot arm. Then the moment it picks another wafer, dia akan melekat, dan the moment it places the wafer to some other module, wafer tu macam masih melekat dekat robot arm, and then the moment it withdraws the arm, the wafer melekat dan jatuh, pom, pecah, wafer breakage. Okay, so that's why the bit needs to be cleared at the circumference of the wafer. So we call it as edge bit removal, ABR. Right, so that's it for today. I'll continue tomorrow with the rest. Kalau habis tomorrow, then we're gonna move on to etching. Okay, is the next process in wafer fabrication. Any questions so far?
No.
Good, semua faham? No question? Right, before I forget, your test 1, will be conducted, sekarang week 7, right? So we're gonna have our test next week 8 on Friday for 2 hours. Okay, Friday 10 to 12. Hopefully everything is okay, no issues. Friday 10 to 12, 2 hours, open book. Right, you're gonna be given 3 questions to be answered in 2 hours. Okay, open book test. So we're gonna cover from the very first topic until lithography. Okay, first topic sampai lithography semua. So write 3 questions in 2 hours, open book. Okay, just like the way we did for 386 last time. So then you are required to send your submission online dekat eLearn in PDF for me to continue. Right, any question? Test 1, that will be 20% of your overall coursework mark. Dan jangan lupa assignment 1 is due on the 10th, right? On the 10th. This week, Friday, isn't it? 10. Yeah, Friday. Friday, 5 p.m. assignment 1 on eLearn as well for submission. Then test 2 next week, Friday 10 to 12, open book, 3 questions, 2 hours. Okay, ada soalan? All good? Right then, I'll see you tomorrow, inshallah. Bye-bye. Assalamualaikum. Take care. Okay.